Sorry, the fella in there says you'll give me a signal and then I can start. Okay, hi everyone. Thanks for coming. Before I begin, maybe I wish to temper expectations a little bit. Okay, I'm from a stats department, so this is a statistician trying to work on LLMs. So maybe don't expect too much. Okay, so what is this? So this is a talk on transfer learning and something about LLMs. What is this aspect of LLMs that we're going to look at? Is a superalignment problem. The narrative behind it that was sort of first made it popular was this idea that in the future, we're going to have these LLMs that are going to perform better than humans at a lot of tasks. And presently, the way that we sort of align LLMs get to do what we want is we have sort of gold standard human labeled data. And in the future, when the LLMs are doing better than humans, maybe this human annotated data may not be enough to properly align them, okay? And so the problem is then in the future, when you are in this setting, how do you develop some way of aligning LLMs with, let's say, just human feedback, or more generally, feedback that's sort of weaker by the standard of the LLM. So in order to sort of look at this problem today, we don't have these superhuman LLMs yet. The analogy that we're going to work with, that this paper proposed and that we are also going to work with is to get a smaller, weaker teacher in the form of like a very small, maybe less than 8 billion parameters LLM, and use it to supervise the alignment of a like a GPT-3 or GPT-4 level LLM. Okay, so that's the superalignment problem. So if you're sort of a statistician and you're faced with this problem, a couple things sort of pop into mind. The first is that in some sense, there's no way for this LLM that's being aligned, this big pre-trained model, to discern between what is a real alignment signal and what is just some mistake that the small model is making because it's a small model. And on the other hand, what gives you some hope is that, well, this pre-trained model is supposed to be sort of extremely good at doing things already. I mean, the whole point that we're sort of in this conundrum is that this pre-trained model has this ability that exceeds what the small model has. And so maybe the way to sort of help the pre-trained model detect the mistakes of the weak teacher is to use some of these latent abilities. And I'll be very formal of what I mean by latent abilities of this large pre-trained model later. That's the, yes, Samurai.
By alignment, I hear the term often. I have no idea what it's for.
Oh, I think that is a great point. This is one of these things where it's just like adversarial examples or transfer learning even. Different people mean different things. I will show you a mathematical formulation of a problem, and then it'll be very clear what I mean by alignment in this context. Any other questions? Okay. So that was the LLM part. This is the standard transfer learning notation setup slide, okay? The only important things I want you guys to remember is that we're going to use P for the source domain and Q for the target domain. This is the standard transfer setup where you have maybe a large number of source samples, a few target samples, and you want to train or find a model that performs well in the target domain. The risk here is defined with respect to the distribution Q of the target samples. The small modification that we need, and this maybe gets into some of the settings that Claire was talking about earlier, is that in this superalignment setup, you only have access to this weak teacher, and therefore you don't actually have access to these gold standard labels from the target domain. And so the small modification we're going to make is that you actually have weakly labeled samples. So you think of them as noisy labels or labels with some type of systemic bias from this weak teacher. However, your goal is still to do well with respect to the gold standard labels in the target. Okay, so the only small modification here, very glibly, is that there's a prime now on the labels from the target domain that's available to the learner. Throughout, this is a bit of notation throughout the rest of the talk, I'll use prime to denote anything that comes from the weak teacher. Okay. Yes.
Are you assuming that NQ is relatively large?
So in this case, yes, there is we don't have this restriction. Yes, there is, I guess, another small point of difference is that in standard transfer learning, you have to sort of assume that Q is small because otherwise you can just train on the target samples. And so for us, we don't need this restriction because even when you have very large numbers of samples here, because they could be noisy, they could be biased, you might still do very poorly. And sometimes you need to leverage the source domain even when you have large numbers of target samples. Okay, so I mentioned this LLM problem. I mentioned this transfer learning setup. What is the connection between the two? So the pre-trained LLM, the one that you want to align, you should think of as this predicted distribution, the source domain. This is what the source model knows. This is what you want to leverage. The superalignment task, right, this goal of what you want to achieve, is defined with respect to the gold standard labels in the target. Okay, so this is the predicted distribution in the target. And finally, your weak teacher, this is defined with respect to the analogy of this is the predictive distribution of the weak labels in the target domain. So you have this prime here. Okay, and again, the sort of the challenge that you don't ever see gold standard labels in the target. Okay, this is the connection between the two problem setups. Okay, so as we heard quite a few times at this workshop already, transfer learning is not possible if you completely make no assumptions about the relationship between the source and the target, right? There has to be some relation in order for you to leverage the source to learn the target. And so this is the specific assumption I'm going to make. I'm going to describe this assumption mathematically, and then I'll maybe justify for why this assumption is reasonable for LLMs. So the assumption that I'm going to make, I'm going to call it latent concept shift, just so that I can keep referring to this later on. The idea is that the predictive distributions in the source and the target, they are mixtures. Okay, they are mixtures of the same collection of mixture components, but the weights are different. Okay, and just to keep it quite simple, I'm going to assume that in fact in the target domain, the weights are actually sort of all concentrated on one of the mixture components. So one of the mixture components is the target predictive distribution, and then you sort of mix in all these other distributions in the source. Okay. So Samri, this is sort of what I mean formally when I talk about alignment, is that I want to let these weights. That's the mathematical reduction. Okay. To make my life easy, I'm also going to assume that MP is extremely large. So I just know this distribution. I'm not going to worry anything about learning. Okay. In fact, for a lot of the rest of the talk, I'm not going to worry about sort of rates of convergence, because the real quantities, the real questions that come up with these questions of bias. Okay, and that's what we're going to be mostly working with. And so with this sort of assumption, you can sort of imagine that essentially this is taking this alignment problem and boiling it down to this sort of, I would call it a deconvolution problem. You have this mixture, you want to learn the weights. And this idea will come back, this algorithmic idea will sort of come back when we devise algorithms. But before we go there, let me maybe justify this assumption to you a little bit. So this assumption is called, it's motivated by this, I guess I would call it a latent concept model of LLMs. I don't know if people actually sort of formally call it this, but in light of the actual content of the assumption, I think this is a name that makes a lot of sense. So let me walk you through what this assumption is saying. So you have a LLM, and this is the predictive distribution. So this is the inputs, and this is the predictive distribution over the next token. Okay, and essentially what it says is that this predictive distribution is a mixture, and it's a mixture whose mixture components, I'm going to call little g, you can interpret this as sort of the things or the tasks that the LLM knows how to do. Okay, and then you have this prior pi, and this prior pi is essentially saying, given the input, I will now look at the list of things the LLM knows how to do based on my prompt, and then go and execute that thing. Okay, this is sort of in some sense the two-stage sort of probabilistic interpretation of what this model means. So let me maybe run through an example. So these tasks that this LLM knows how to do, you sort of index them by these ideas that you call them concepts. Okay, and so for example, here maybe two concepts are nationality and occupation. Okay, and each of these again is going to index a task or an ability that the LLM has. In this case, it will be nationality prediction or occupation prediction. Okay, so I look at this G function in the middle, which again encodes the abilities of the LLM. And if you give it the exact same prompt, so for example, Isaac Newton is, but you pass it the nationality concept, then it's going to say Isaac Newton is English. Okay, but if you take the exact same input, but you pass it the occupation concept, it's going to say Isaac Newton is a scientist. Okay, this is formally what these abilities and what these concepts mean. And the way that we think about this, that these G's, these are the LLM's latent abilities. Okay, that we're going to try and elicit. Following my comment on the first slide. Okay, so now you can sort of see where this latent concept shift assumption comes in, right? Essentially, this first part of the assumption, it basically says that the pre-trained model sort of satisfies this latent concept model. The capital G's here, they were the little g's in the latent concept model, right? And the weights, they were the pi's. Okay, and again, this assumption here just says that Well, what is the goal of my alignment task? Is I'm trying to elicit one of these latent abilities. Yes, Nati.
You had what you had before is the weights were dependent on X, and here they're not. So I mean, how should I think about it, or what? I mean,
oh yes,
it seems the previous one seems to be the more natural one than here.
No, that is true. The way that sort of we think about this is that this is maybe a slightly more restrictive version of the assumption, because this mixture in some sense is not really well identified. And so the way I think about this is, for example, I want my LLM to, the classic example that we sort of think about is I want my LLM to write code in a particular style. I want it to write comments. I want it to index like this. And this data is encoding this style. Okay. And so you're always wanting to get it to write code in a particular style. Does that make sense?
But what should I think? What's X in that case?
X would be like the GitHub issue that you're sort of shoving into this thing. And you want it to output code in a particular format. Yes.
Say that
There's two collinear people.
just to say this is the standard model underlying the mixture of experts, right? So the I is the gating model.
This one is.
This one is.
Yeah.
Yeah.
But
So,
not
it's, so the other one is like, yeah, just ignoring X and saying it's a flat prior.
Yes, that is what I mean. Did you have another question?
Yes, quickly, I was going to say that, I mean, why is it that Q, the target, would not be also a mixture? In fact, in practice, in a variety of cases for fine-tuning, you would want to think of the target as a mixture of potentially previous tasks. So
I think everything that I'm about to say will go through if you don't assume this to be a single task. In fact, in the more sort of general theory that we do, we sort of don't assume that you have this mixture weights concentrated, but just for interpretability's sake, maybe. Any other questions? Okay. So we have this sort of connection, this model set up. What are we going to do? So the first thing maybe is let's think about, use this theoretical setup to think about what people usually do. And what people usually do for the superalignment problem is they simply take the weak teacher's output and they fine tune a strong model on it. Okay. Don't look too much into this slide. This is just a picture that I put here because I wanted to talk about fine tuning. Okay, sorry. This is, maybe I'll say one sentence. This is the picture that this original paper that studied this fine-tuning strategy used to present fine-tuning. Hence, I am using the same picture. So in order to do a little bit of theory and make our lives easier, let's even simplify the problem further, okay? So let's look at regression. So I'm gonna look at fixed input regression. And so that's my matrix of inputs X, rows are the individual inputs. And then I have two vectors of output. So one is, you can think about what the source model thinks, YP, and YQ prime, this is gonna be what the weak teacher thinks, okay? And in this setting, your latent concept shift assumption boils down to something like this, where you can essentially say that the regression functions in the source and targets, they themselves are mixtures. This is what it boils down to. And to make my life easier, this assumption that you know the source model boils down to the source model being here, YP being drawn directly from the regression function in the source. And also to make my life easier, because we're actually going to show a negative result. So the more sort of assumptions I sort of help the setting as it sort of strengthens the result, I'm going to assume that the weak teacher is actually unbiased. So there's no systemic bias in the output of the weak teacher. Okay, it's just extra noise that's added. Okay, so what do you want in this setting? Well, the learner seeks a model that ideally does two things. One, it should do better than the strong model, right? The completely unaligned strong model, if you just gave it the inputs, what would it do? And the second thing is that it should do better than the weak teacher. Because in either case, if you don't, then you can just either deploy the unaligned strong model or deploy the weak teacher. This seems like a very obvious point, but as we will see, this may not be was not so obvious at the beginning. Maybe the way to think about it is that when you sort of think about this problem statistically, it becomes very obvious. So you have this regression problem, we have this complete probabilistic setup. You can just, this is like maybe a homework problem for your first year PhD, regression class, and you can work out, what the argument is, and you can work out what the MSE of the strategy is. And it turns out that it's not surprising. The MSE is just this sort of combination of the MSEs of the pre-trained model and the weak teacher. Okay. Oh, sorry. I skipped the slide. I should say, what is the analog of fine-tuning here is I'm going to essentially find a model that both has small discrepancy with respect to the weak teacher and a small MSE with respect to the strong pre-trained model. You can think about so alignment strategies like RLHF, they will explicitly have a term that regularizes you towards a strong model. If you don't use RLHF, you use something like just fine-tuning, then you can think about this regularization towards a strong model as implicit. Okay, but this is going to be my analogy for what people do. This is what I was talking about earlier. If you work out what the MSE of this estimator is, essentially boils down to some type of mixture of the MSEs of the source model and the MSEs of the weak model. At this point, what should sort of strike you is that this is in some sense incompatible with these goals that we just set up. I want to beat the strong model. I want to beat the weak model. But if my MSE is some combination of the two, then in some sense, I can never do better than the best of both of them. Okay. And this is something very obvious, simple regression analogy. Again, temper your expectations. But let's look at whether does this play out in practice. Okay, so we again went to the original superalignment paper, and this is sort of how they presented their results. So let me just unpack all these bars for you. So here, we switched from lost accuracies here, so higher is better. Okay, so on the left side, so these are sort of different tasks, but they all sort of follow the same pattern. On the left side, what you have is you have the performance of the weak teacher. Okay, this light gray bar. Green is the performance of fine tuning. Okay, and generally, you do better than the weak teacher. The purple thing is something that it's a form of fine tuning, but there's an additional regularizer, some type of entropy regularization. But the way that sort of I think about it is that it's it sort of falls into this fine tuning family of methods. Okay, we were not able to reproduce these results because, well, when I show you the experiments, it'll become obvious why we couldn't reproduce these results. It's mainly an infrastructure problem, but so I'm not going to focus too much on this purple bar going forward. Okay, and finally, this dark gray bar, you can think of what this is. This is hypothetically what you would have gotten if you took the strong model and you directly fine tune it on gold standard labels. So this is, in some sense, the performance ceiling. Okay, so these are the results that were presented in the original superalignment paper. What is notably missing here, right, is what is the performance of the strong model if I just don't fine tune at all, like just the raw performance. And so, okay, we didn't repeat all their experiments, but we did it for one particular set of experiments, the math reasoning experiments. And so here what we're doing is we're using various weak models, so Gemma, Llama, Mistral, and the strong model we're using is GPT 3.5 Turbo. Okay, we were using sort of OpenAI's API to sort of fine tune, and that's why we couldn't sort of have custom sort of fine tune solutions. We're just using their default fine tuning. And if you run this experiment, you take your weak models, you produce these weak labels, and you fine tune GPT 3.5 on them. This is what the performance of this fine tuning looks like in relation to this is the strong teacher. Sorry, the strong pre-trained model. This is the weak teacher. And by and large, you see they're kind of in the middle. And this is sort of, agrees with what the theory tells us. You can't do better by just fine tuning. Okay. So this very sort of simple regression analogy, surprisingly, maybe generalizes to this generalizes to practice, I guess. Okay. So how do I fix this? This goes back to this idea earlier of maybe deconvolution, right? I said that you want to learn these weights, so it boils down to a deconvolution problem. Well, ideally, if I knew what these mixture components that are trying to deconvolve were, and what I would do is this would be like, as a statistician, this would be like the most natural thing you would do. You would minimize the discrepancy between your weak teacher and the model that you're currently trying to train, and you would enforce this prior assumption, this structure that this model satisfies it with some set of constraints. It's like the most natural thing you would do. Right? Do you have a question?
Were you restricting to the convex file, not to just one of them? Is that, I mean, you,
Oh, I guess you could also restrict to just one of them. That would sort of make the result even better. So yeah,
it's,
yeah. There's some. I think what you're seeing is this discrepancy between what you try to do theory. We try to account for the case where the prior is not just the prior is not just concentrated on a single task in the target domain, and that's why you see sort of theory like this. But yes, if I were to sort of perfectly match it up, then I would, I would put it to just one. Yeah. Okay. So you would like to do this, and so as a statistician, this sort of warms my heart to see things like this. These are, your Gaussian widths. Maybe here things are not Gaussian, so maybe we can't interpret it as a Gaussian width, but we like sort of things that quantities that look like this. But the punchline is, if you look at the resulting MSE of this type of an estimator, you first notice that the performance of the source model has completely disappeared. This epsilon p term doesn't appear at all. So you're not really bound or affected by the performance of the source. And the second thing is, you can really beat your target. Right? You can do better than your target. Okay, so in some sense, if you look at this type of deconvolution estimator, then these limitations are removed. Now, the problem, of course, is that you can't actually execute this deconvolution estimator because I do not have access to, in order to execute this deconvolution estimator, in order to even construct it, I need to know what my latent abilities are. And these abilities are, well, latent. So I don't actually know what they are. So the challenge is now, how do I sort of take this idea and maybe operationalize it in language models? Okay, and so what we're going to do is in context learning. And this sort of, I should say earlier, this latent concept model was one of these models that was used to sort of explain or describe what is actually going on under the hood when you do in context learning. And this is where this idea comes from, actually. So at a very high level, the theory for how the results say something like this. I have this latent concept model. If I go to one of my abilities, one of my tasks, and I draw XY pairs in context learning pairs, and then I simply pass these pairs as a string in the prompt to my language model, then what the language model will do, what conditioning on these in-context examples is effectively doing for me, is concentrating this prior on the correct task. So on the task where you're drawing these samples, conditioning on these samples will concentrate this posterior predictive distribution on that task. That's a super high level summary of what this Bayesian explanation of in-context learning is doing. Okay. So what we're gonna sort of hope and pray, okay, is that instead of getting these quote unquote gold standard labels, right, for my actual task, if I just replace it with the weak teacher, life would be good. Okay, if I just replace it with the weak teacher, life would be good. The implicit assumption here, of course, is that when I do this, right, when I replace these strong gold standard labels with the weak teacher labels, that my strong model must be sort of strong enough to accept the additional noise. Okay, and this will come out in the theory if I have time to get to it. Okay, so Martin, do you know how much time I have? Sorry. Oh, okay. So here, what I'm sort of showing you is sort of maybe a graphical description of what this what I'm sort of hoping this in-context learning algorithm is going to try and do. So let's say that I want to teach this LLM to always respond when I prompt it with a name with this person's nationality. Okay, that's what I want to do. If I just go to the model and say, ask it to complete the sentence Taylor Swift is, these are the things that it comes up. This is actually not a real completion. I just went to sort of Google and did autocomplete, and that's how I got these. But I'm just trying to make a point here. And this is for illustrative purposes. So if you go to Google and you type in Taylor Swift is, and these are the completions. Is it now over? I think is a song. Is dating Travis Kelce, is engaged, and a bunch of other stuff. But you see American also appears. Okay, and this is what I wanted to respond. But it's not sort of, and hypothetically, the distribution, again, these are all made up. It's not the leading response. Maybe people like to search for this song, and so this is the leading response. Okay. The whole point is that I go and the idea behind this algorithm is I have this set of in-context learning examples that is a combination of, let's say, other people's name and nationality. So I'll put like Albert Einstein is German. Isaac Newton is English. Now I have a whole list of examples like this, and I shove it in here, okay, into the prompt. And then I ask again, Taylor Swift is, and it will say with overwhelming probability, American. Okay, this is the graphical depiction of this in-context learning mechanism. And the whole point is that even if you put in some pairs with mistakes here, let's say there's a Albert Einstein secretly was American, you put one of these mistaken samples in here, it will still do fine. It will still sort of successfully infer that you're trying to infer nationality and still complete the sentence with American. Okay, that's the hope. That's what we're sort of the mechanism that we're relying on. Okay, so the key thing about this mechanism is that yes, I wanted to, my alignment task, as I sort of formalize this, I want to learn this prior over the abilities in the target domain. I'm sort of explicitly trying to avoid doing this because in order to actually learn which target task is important, I need to know the latent abilities. And here you can think of this ICL example is effectively trying to denoise, trying to sample from the correct target ability without actually doing the work of inferring the target ability. Nowhere do I ever learn this data Q quantity. Okay, and this is sort of what allows us to get around this issue of not knowing of the target abilities being latent, of not knowing them when we run this algorithm. Okay, so let's complete the setup, complete the algorithm. You're given a weakly labeled data set. What do? You go to, for every single input in the data set, you are going to maybe select a subset of weakly label examples, maybe with k-nearest neighbors or something like that. And then you're going to use this as a prompt, and you give it to the pre-trained model. The pre-trained model will return an output, and this is your improved or refined output. Okay, and now you've got to do this for every single data point in your weakly labeled data set. You have this collection of refined outputs, and this is what you're going to fine tune on. Okay, this is the most basic algorithm. You can think of endless variants of this, but this turns out to be sort of the easiest to think about. And so this is what we'll go with. So this is the algorithm. Okay. It's to improve the labels of the weak teacher and then fine tune on them. Okay, so now let me show you the rest of the experiments that we ran. So we used two sets of pre-trained models. These are 3.5 turbo, and later on we added Oracle Mini. These are the weak teachers that we use. They're generally open source models that we could sort of fine tune ourselves with the resources that stats departments have. And finally, the reason why we do not use, okay, at that time, the latest and greatest models was GPT-4o is because we wanted to hold it out as an evaluator. Some of these have open-ended outputs, and I need this thing to tell me if this thing is correct or not. Okay, so maybe I don't need to give these slides, but usually I give this talk to stats people, so I have to explain to them what all these data sets are. Are we okay if we just skip ahead? You guys all know what GSM-AK is? Maybe I'll skip this. GSM-AK's data set looks like this, okay? You have some math problems, and there's some reasoning steps, and there's a final answer, okay? And this is one of the tasks that we sort of tried to, this is when I said earlier, referred to a math reasoning task. This is one of the tasks that we're looking at, okay? So you want this model to, the idea is sort of, if you don't sort of tell align a model so that it reasons, it will oftentimes just try and spit out the answer, and then it will be wrong a lot of times. But if you sort of prompt it in such a way that it sort of starts to sort of think through its steps, then the accuracy drastically improves. That's the alignment task here. Okay, so I guess there's not really too much to say on this slide, except the key punchline is that if you do this type of, you first improve the labels and then you fine tune, you can actually beat, in this case, this is the weak teacher, and this is the unaligned strong model. And purple is the performance of the ICL algorithm. So I was showing you just the light gray, teal, and dark gray bars earlier when I was talking about the inadequacies of naive fine tuning. And so here I'm just sort of filling in the performance of this refinement algorithm. Okay, so I don't want to sort of say that this algorithm is like some magic bullet. It doesn't work all the time. Okay, so here is a notable failure case with Llama 7 billion. We'll see some more failure cases in a little bit. So the other data set that we tested was, so GSM-AK is sort of grade school math problems. So these are by and large becoming kind of easy for these frontier models. And so here's a harder problem. Sorry, a harder data set. It's the same idea, but you just have harder problems. Okay, and these instead of grade school math problems, these are like high school contest math problems. That's what these are. I find it very funny that they subjected a PhD student who does not like math to this exam just so to get this number. And they were very clear that they could have just said a CS PhD student, but they had to say a CS PhD student who does not like math. And so I just find, yeah. Anyways, so this is a much harder task. So you can see that performance are by and large lower. But with GPU 3.5 Turbo, we still sort of do better. But with 4.0 Mini, it's getting pretty hard. Okay. We have some explanations of what could be going on here, but let me present for you the theory, and then maybe we'll get to the explanations. But by and large, still, you're still doing better than naive fine tuning. So I still count this as maybe half a win. Okay, so in the last little bit of a talk, maybe I'll say, since, so we sort of posted this, there's been other work that sort of also explored this refinement idea empirically. And these people have come with sort of just more sophisticated ways to refine, basically. You can imagine, you can prompt the model, right? You can provide a model with a list of principles or a list of topics that it's going to select from. You can try all kinds of different sort of flowchart type techniques, combine them. But what I'm trying to get at is I don't really want to sort of think about what all these get into the details here. I want to sort of maybe think about the question whether this high-level refinement approach is the correct way to go about this problem. And if I don't have time to get to the end, the answer is no. There's a gap, and so, but I don't know how to close it. Okay, so how am I going to think about this problem, right? This problem of whether refinement is optimal? I need to sort of complete the probabilistic specification of the problem. Okay, so in our problem, there are, in this case, 4 variables. There's X, which is the input, theta, which you can think about as this latent concept that's indexing what ability I'm trying to elicit from my model, Y being the gold standard label, and Y prime being the weak output. Okay, I'm sort of inputting this theta in also as a random variable because it'll allow my probabilistic reasoning steps to go through. Think about it as a random variable. So what I'm going to assume is that you have source and target, okay, and they both have this structure. So the conditional independencies in these distributions factorize according to this graph. You have an input. The input tells you sort of what to do, and then this sort of becomes you have one arm in some sense that generates the gold standard output, and you have another arm that generates the weak output. Okay, so basically the idea is the assumption that's sort of being made here, right, is that given X and theta, my weak label, my strong label, these are conditionally independent. Okay, that's the assumption. That's the probabilistic assumption that's being made here. The other thing that I'm going to assume, again, I have to make some similarity assumptions. What I'm going to assume is that the P of X factor, so the marginal distribution of the X, and this conditional distribution of Y given X and theta, these factors are the same in the source and target. So you remember there are 4 factors, right? So this, sorry guys, there are 4 factors. So this factor is the same, okay? This factor is the same, okay? These 2 factors are going to differ between source and target. That's the assumption. So I first set up this transfer learning problem. Now I'm giving you a new set of transfer learning assumptions. They are related, okay? And you can just sort of look at the intuitive takeaway from this picture. That if I look at one of these arms, maybe I just ignore the other arm. Now what this essentially says is that the predictive distribution, let's say, look at this arm, it is a mixture, okay? Just like before, same type of assumptions. The slightly weird assumption, maybe that some of you have picked up on, is that the assumptions that I made are not really symmetric, right? I assume that this factor is the same in source and target, but I did not assume that this factor is the same, okay? So where is this assumption coming from? Maybe actually, let's skip to the next slide. The assumption that the source factors are the same, you can essentially think of so I think of the source model, okay? The source domain, P, as basically any model that's maybe trained on this data set that does not have this special alignment task baked in. And then Q as the distribution of data that has this alignment samples built in, okay? The idea that these 2 parts are the same essentially is saying that in my source distribution, hypothetically, right? I could have given the strong model this gold standard labels, and this is what it would have. This is what it would have output. It's Q. Okay. Hypothetically, that's what it would output. The bottom sort of the bottom arm where they're different. Essentially, in the source, what this is saying is, what does this? Actually, maybe I'll start with the target. In the target, it's easier to think about this. This is basically what the weak teacher sort of how it's generating its outputs. It's a bit more confusing to think about what is in the source. The way I understand is that in the source, you should think about this as how this source model is sort of simulating the weak teacher in some sense. Okay, and the source model needs to know this because remember, I'm going to use the source model to correct the weak teacher's mistakes. So the source model needs some like internal representation of what the weak teacher is doing. And you can think about this as what this internal representation is. Okay. What is the analog of refinement? Well, in my algorithm, right, what you say is you get a input from the target, you draw your ICR examples, and then you refine it. So here, refinement I claim is sampling from this distribution, which I'm defining like this. And again, right, I get my input, I sample a weak output. This y prime you should think of as you should think of as maybe a collection of these y primes, and then I condition and I refine. I draw a sample. Okay, this is the probabilistic analog. Just so that I end on time, the punchline is that you can actually work out what this quantity is using the probabilistic assumptions that we had before. And what you see is that it's not quite Q of y given x. Okay, so that's the first thing, which is the first fact. This is what you actually want. And the second thing is that under some more sort of technical assumptions, you can show that this quantity is actually identified. Okay. So that means that at least information theoretically, the information is there to learn this. But this is never going to learn this. It sort of always has some bias term. Actually, this goes back to Clay's talk. There's some irreducible error. You're never going to close the excess with this technique. And so what is the intuition behind this result? Well, it goes back to this deconvolution idea, right? If you can actually solve the deconvolution problem, that's how you're going to sort of do this type of identification. The identification restrictions are essentially these type of mixture identification restrictions of the mixtures that arise in my source and the target. Okay, and so if you could solve the deconvolution problem, then you could get this, and that's that in some sense is the gap. Actually solving the deconvolution problem versus this cheap surrogate that I got. Okay, so that's it. I guess the main point that I wish to make are one, if you just naively fine tune, you're in some sense not going to get anywhere, but there is a way to get somewhere. You can do this refinement type algorithm. However, this refinement algorithm doesn't seem to be optimal, so maybe there's more you can do. Okay, papers on archive. Thank you guys for your attention.
So we have time for a couple of questions from the audience.
I had a question about the algorithm. So do you pre-train the GPT on the source data and then ask the in-context questions? Or what is it trained on?
So you're talking about this algorithm?
Yes.
Oh, so the pre-trained model is just pre-trained. It's like GPT as OpenAI publishes it.
Oh, okay.
Yeah.
So can it be viewed as maybe softening the labels in your target data? Could you simulate this by putting a kernel?
So I'm not sure what you mean by softening, but I guess I do wish to point out that the way we think about these weak labels is they're not just sort of maybe noisier versions of the true target. Like you allow them to be there to be some bias. Sorry.
And does your theory actually support this claim?
Yeah.
Or?
So, well, I don't know about whether your theory supports this claim. There is a lemma which I kind of skipped over, which is that it's my sanity check lemma. Statisticians left sanity check. So remember, I said that there are these two parts, right? There was one which is what the weak model's abilities actually are, and then there's a strong model's sort of model of the weak model's actual ability. So if these two things agree, right, then regardless of whether there's bias, regardless of whether there's just noise, then refinement always helps. It always improves.
Right.
And so you do allow for that.
Thank you.
Thanks for the talk. What
Hello.
is the KNN doing there? Is it in the input space or in the embedding space? For the Taylor Swift example you gave, I was curious what the KNN would return there.
Oh, the Taylor Swift example? Where's the Taylor Swift example? Ah, here it is. Sorry, what was your question about Taylor Swift example?
So you're building S prime with a KNN, right? To the
Oh, what is S prime? S prime is just a bunch of pairs like this. You could handwrite these if you want to.
But you're obtaining through KNN, you said. KNN of X.
Oh, for here, I did not do canon. I just, I imagine you just write these yourself.
Yeah, my question is like, how do you do refinement? You're acquiring some
Oh,
through KNN, and is that KNN in the embedding space, and what exactly it would return for this example?
oh, you mean here inside this to generate this set?
Right.
Yeah. So you could do it in the embedding space. So there are actually a lot of cases where your weak teacher only has a very few examples. Because let's say you're like, remember the whole motivation for this problem is that humans are like providing is your weak teacher, right? And so oftentimes you don't even need to do canon at all. You just shove the whole set of weak teacher examples in as your S. But in cases where, let's say, for the math data sets that we saw earlier, yes, you do sort of restrict because you can't fit all the examples in context. But I just want to emphasize this is in some sense like maybe a slightly sort of artificial thing that comes up because of the analogy that we're studying instead of the original problem.
So in the interest of time, sorry, we should take the other questions offline, but let's thank Yuekai again for a nice.
Also, just wanted to say, okay, we're a bit over time, so we'll try to shorten the break. So let's restart at 11:05. So rather than exactly then 20 minutes, we have it.